Here's an example of a best fit line that was calculated on a computer using software like Minitab or DataDesk or something like that. In the example, a pediatrician collects data on a child's height in centimeters at different ages in months, and is basically trying to see how the child is growing over time. And a least squares regression, if the data are put into a computer, would yield the following. And this is a pretty standard format for a lot of computer output when least squares regression lines are calculated. And some parts are, just occur, regularly in these different kinds of output. Right up here it says the dependent variable is height. That is your y variable right there. Okay, the dependent variable, it's the response variable. Over here we have this word predictor, and in this column we have our x variable is age, and the constant is basically a placeholder for the y-intercept of our line. So you might see, instead of predictor, you might see the word variable written there, and you might see it either way. In the column next to the predictor or variable column, we have this coefficient column, and we have two numbers. This number right here is across from constant, so this is the number that represents the y-intercept, or a, in our regression equation. And then this number right here, the 0.391, is the coefficient that goes with age. That would be our b, or our slope. Next to that column, we have these standard deviations. These are not the standard deviations of x and y. These are actually the standard deviations of the estimates that we have here for our coefficients. So that's something we're not going to have to look at yet. That'll come up much later on as we study regression inference. So for now, you don't have to worry about what those mean. This right here, this S, this is the standard deviation of the residuals. And it kind of gives an estimate of how much a typical data value varies from the predicted regression line. This has a special name. It's called the standard error about the line, but we'll worry about that later on too. This right here, this r squared, that's the familiar r squared that you've seen before. And then right here, this n, this is the number of observations that we have in our data set. So measurements were taken 12 times on this child. And when those measurements were taken, the child's age and the child's height were recorded. And so we have 12 observations. Okay, so typically this is what you see in computer output. We also have these columns for t ratio and p-value, and later on when we study regression inference, we'll fill those in and make some sense out of those things. But for now, you don't have to worry about it. If you have output like this, you have enough information to write the equation of the best fit line, or the least squares regression line. And the way you do that is you write the y variable with a hat equals a plus b times x. So it's just height with a hat equals 72.51 plus 0.391 times age. That's all there is to it. You're basically just copying things out of the computer output and writing them in this format. That's pretty much all you're doing. The slope of the least squares regression line is this number right here, 0.391. And what that means in this context is that on average, predicted height increases 0.391 centimeters for each additional month of age. That's roughly 4 millimeters per month is the estimated rate at which this child is growing. If you're asked to identify the y-intercept and interpret the y-intercept in context, well, the y-intercept is the 72.51. That would be the value of predicted height when age is equal to 0. So we could say at 0 months of age, that is at birth, the child's predicted height is 72.51 centimeters. R squared in context, well, R squared was 96.3%, and that means 96.3% of the observed variation in height is explained by the least squares regression of height on age. So this is the same as always. R squared represents the percentage of the observed variation in our response that's explained by the least squares regression. To calculate the correlation, well, we take the square root of the R squared. That's all we have to do. And we have to be careful in this situation that we take the proper square root. If the association is positive because the slope is positive, then we want the positive square root of R squared. If the slope is negative, that is b is negative, then we want the negative square root of R squared because R would have to be negative in that situation. And if you take the square root of 0.963, you get about 0.981. That correlation indicates a strong positive linear association between height and age. And the predicted response when the explanatory variable equals 50. Well, we can find that just by plugging in 50 for age. So we take our least squares regression line, plug in 50 for age, and then see what that adds up to. That's 92.06 centimeters. So that's the predicted height at the age of 50 months for this child, somewhat less than a meter.